Okay, when the force changes, we need to find the work by calculating the area under the graph of the force times the cosine of theta, which of course we're used to just doing, not necessarily the cosine of theta, but the part that's parallel to the displacement. So the part that does work on the y and displacement on the x. And if we graph that, what we need to do then is find the area under the graph, and that is the work. So for instance, if we keep the force at 1 Newton and the displacement at 1 meter, every box, every square is going to be 1 joule. And we add up the squares and under the graph, and that's the total joules of work. So as an example here, I might take 10 meters of displacement, 1 Newton of force, and that doesn't take up the whole square, so it might take half of that, all right? And then I would start squaring off the rest of it, and adding up squares and saying, okay, well, the area here, now I've got a whole box or a whole square of 10 meters times 1 Newton of force, so 10 joules. And then I would just keep doing that until I had the whole area under the curve calculated. Now your homework is a lot of boxes and triangles, and so you know how to do the area of those. And that's all you do. So, these are pretty simple problems. You just take the force times the displacement, the area under the curve that they draw for you. And like I said, I'm not going to do any of these curves. That'll be triangles and squares. And you find the area, and that's the work in joules. Now, those of you who are in AP Calc BC have done integration. And you know that to integrate is to find the area under a curve. So obviously if you had a more complex curve, if you had the formula, you could calculate it, but we're not going to worry about that. You don't need to know it, obviously. Okay, the next thing we're going to talk about is the power, the rate at which work is being done. And so we're going to add just one more step to this whole work thing. We're going to take the work, we'll calculate it just like we've been calculating it, and we will divide by the time that it takes. Now that is going to give you units of watts. You also can get it by taking force times velocity. So both of those equations are on your sheet, so just kind of be careful with that. Depending on the problem, just look at the units and realize that that's what's going to happen. Because if you look at this, I'm not going to explore it too much, but if I take force, which is in newtons, over velocity, which is meters, or times velocity, which is meters per second, newtons times meters is joules. So it's the same thing. The other thing you probably want to know about is that a horsepower that we're used to talking about power in is equal to 746 watts. Okay, so some examples of I run up the stairs, slow or fast, doesn't matter. I do the same amount of work, but power-wise, I'm going to do less power here and more power here. So as an example, they talk about here, the engine isn't going to do twice the work or go twice as fast if it's twice as powerful, but it will do the same amount of work in half the time. So let's say, as an example, that a liter of gasoline can do a certain amount of work. Say it can do 100 joules of energy, but the power could vary. A car could use that 100 joules in 2 seconds, producing 50 watts of power, whereas a jet airplane would use that 100 joules in a much, much shorter time for a lot more power. So let's just look at an example here. What work needs to be done if I'm going to take a 193 kilogram curtain, raise it up. Now let's get the force due to gravity. So that's the force due to gravity. And if we want the work done by gravity, we have to multiply it by 7.5 meters. So I've got F sub g here, and I'm going to multiply it by distance, so I have the work done by gravity. Now, we're going to do it at a constant speed, so we don't have to worry about kinetic energy changing, but we do have to work against gravity. Now, that's the work. Now, I want to do this in 5 seconds. So when you calculate this, you're going to come up with, let's see, 2,837 watts. Now, of course, a kilowatt is 1,000 watts, so we're looking at 2.8 kilowatts. So if I had to choose a curtain, it'd probably be, that power motor to raise the curtain up, because you don't want to go too fast, you don't want it to go slow, you want just that timing right there. So probably I would choose that. A little more powerful than I need, but good enough. So just as an example of, let's say the curtain was not going at a constant speed, we were accelerating upwards. Well, what we'd have to do is add the kinetic energy requirement in, and then we'd get the total work, and then we could get power. So let's take a look at that. Oh, something else, of course, we should think about is friction. What would happen if the engine had to work against friction? Now, again, don't get the two ways confused. Would you subtract friction? No. We want to add friction to get the total energy. So let me show you how that would work. Let's say that we have a 250 kilogram helicopter starting from rest, rising straight up 12.5 meters, accelerating constantly until it reaches a speed of 5 meters per second. Okay, I am actually going to want to have a time here too, and I should have put that in here. But, just with, your kinematics, you can really quite easily calculate that would take 5 seconds. If you knew you had to go that distance, starting at 0, getting to 5 meters per second, you could get the acceleration, you could get the time. So I should have put that in there, but time is 5 seconds, just using a kinematic. Let's say that you're going to encounter 2,000 joules of frictional air resistance that will work against the motion. What is the power? Okay, so I'm going to go ahead and find the work first. The work that the helicopter needs to do, and I'm going to call that an applied force. Plus, it's going to work against friction. This will be a negative 2,000 joules, okay? But those non-conservative forces are going to equal the final mechanical energy minus the initial mechanical energy. So I'm going to take the final mechanical energy and the final potential energy, and I'm going to subtract the initial. Now this helicopter starts on the ground, so it starts with nothing, but it does reach, it says 5 meters per second. It will reach a height of 12.5 meters, so it gets something, and it's going to get it from the applied force, which is a non-conservative force, and of course it has the friction force, which is also non-conservative. So I'm going to go ahead and find the work done. And what I'm going to do is I'm going to take this negative 2,000, I'm going to add it over here. All right, so I get a 250 kilogram helicopter. I'm going to get it up to 12.5 meters per second. Square that. I'm also going to get it up to 12.5. Oh, gosh, I cannot believe I did that wrong. I am so sorry. It goes to 5 meters per second. But I unfortunately am not going to re-record this, so sorry, kiddos. All right, so 5.0 meters per second, and it goes up to a height of 12.5 meters, plus, of course, that 2,000 joules of energy. Now, I'm going to take that total work. I'm going to divide it by the time that it takes for this all to happen, and we are going to get a total power of something, should calculate it, 67,900 watts. Watts of power. And I'm going to call that power. Power due to the work, due to the force. So 67,900 watts. Okay. Last problem, and this is going to be on the test, and it is so easy. I really, really, really want to make sure that you understand what's going on here, but it's so easy. A megawatt, this is a megawatt, and 1 times 10 to the 6 watts are in a megawatt. Mega means billion. Okay. And so what we have is 3.5 times 10 to the 7 watts. Now, the biggest thing here, just one little hurdle, you have to remember, what is a watt? A watt is a joule per second. So all I'm going to do is if I run this power for 1.5 hours, and we know that 1 hour is 3,600 seconds. So basically what we're talking about here is 5,400 seconds. So I'm just going to go down here and multiply by seconds. Seconds will cancel, and you will be left with the joules, which is 1.9 times 10 to the 11th joules. Okay, so make sure you take your watts, get them into joules per second, multiply by the seconds that the engine runs. The seconds will cancel. You'll be left with joules of energy. Okay, that's it. Try some of your homework problems. Check the solution guides up in front if you're really having a hard time with it. But if you pay attention to units, you'll probably be just fine.